Okay, so in this next set of videos, I want to do a crash course on complex numbers. I'm just start from scratch, I think, so that we're all on the same page. Um, Complex numbers are really, really important, not just for our story of what do you do when your characteristic polynomial has a negative discriminant. Remember, when we're talking here in the context of second order homogeneous linear differential equations with constant coefficients. When your um, discriminant of your characteristic polynomial has a negative discriminant, then you have to deal with complex numbers. Um, like I say, the complex numbers, it's going to be worth it because complex numbers play a role in much greater context than just this very narrow role. So it would be useful for you and your life to learn about the complex numbers more generally, and that's what we plan on doing here. Okay. All right. So first of all, what are they? What are some of the notational elements that go into, let's say, complex numbers here? So first of all, the complex numbers as a collection of numbers are oftentimes written in the following way. It's a sort of fancy C. Okay. Now this is the contrast with a fancy R. Um, Maybe you recall R, something like this, is given by the set of real numbers. And C is certainly related to the set of real numbers. In fact, we will see that the real numbers are kind of embedded inside of the complex numbers. Let me give you the definition of what C is as a set, and then we'll start working with it. And as we start working with them, you will start to develop your intuition around these objects. The complex numbers are, by definition, the set of all numbers of the form x plus I, y, where x and y, and I'll define what I is in just a second, but x and y are real numbers. So I'll denote that state of affairs like this, where, and here's where I'll tell you what I is. I is a number whose square is -1. And it's this property of complex numbers that we can have numbers, complex numbers whose squares are negative real numbers. This is the property that we want to take advantage of when we find ourselves with a negative discriminant in our characteristic polynomial. And we'll see how that comes about in upcoming videos. But for now, rather than having that full blown discussion, let's think about, first of all, how to visualize complex numbers through something called the complex plane. So you can see here that there are two real numbers involved in the complex numbers, x and y. And so naturally, we can sort of plot complex numbers or visualize complex numbers if we set up for ourselves a sort of xy plane type situation. So maybe something like this. So we have uh, this and this. If you're familiar with the xy plane as you learned it maybe in multivariable calculus, no, I'm sorry. Yeah, well, no, sorry. Let me back. Let me take back my apology. Both of them. The apology for the apology. Let me take that back as well. If you learned about vectors, particularly vectors in the plane, it's going to feel very similar. You're going to be able to use that idea to understanding what's going on with the complex numbers. We're going to track what's called the real part. Maybe I should go ahead and define some of this stuff. So if you have z equal to x plus iy, here's just some terminology. We write the real part of z is x, okay? And we say that this is the real part of z. This is terminology now, the real part. And we also write m of z. This is y, and this is sometimes called the imaginary part of z. Okay? And we can track, visualize complex numbers like z equals x plus iy in the sort of xy plane if we say that this is going to be the tracking the real part of z. The horizontal axis is going to track the real part of z, just like the x-axis will track the x component of vectors. And similarly, this will track the imaginary part of z. So in particular, let's say that we have a number like 3 plus 2i. 3 is what's playing the role of x. 3 plus 2i. I know or I times 2. 2i. 3 plus 2i. I don't know why, but I have to put the number in front of the I. Okay? 3 plus 2i. That's going to be the following complex number. 3 along the real axis, 1, 2, 3, and 2 up along the imaginary axis, and we get this number here. This is the number. This is our visualization of the number 3 plus 2i in the complex plane. The number negative 4i. Negative 4i is a complex number. It sits right there in the complex plane. Negative 4i. Real numbers like 5 are in the complex plane as well. Here is the real number 5. It's 5 because it has no, or it's real because it has no imaginary part. Okay, it's 5 there. And this number right here would be negative 3 minus 3i. 0 is also a complex number. It's right here. This is the complex number 0. Okay? So that's how we visualize the complex plane. All right? This is also sometimes called the Argand plane, but whatever. How do we do addition? Complex addition, or addition of complex numbers. This is very simple. I think, very sensible. You just add the real parts together and you add the imaginary parts together. Okay, so for example, if you have let's write it like this: a plus bi, that's a complex number, and you add to that c plus di, then this is equal to a plus c plus b plus di. Right? You add the real parts together. The real parts of this number, the real part of this number is a. The real part of this number is c. You just add them together to get the real part of the sum, and that's a plus c. And similarly, b plus d, bi and di get added together to become b plus d times I. Okay, exactly what you would expect. So nothing strange there. Maybe more interesting is the multiplication of complex numbers. Because here's where we're going to use this fact that I squared is equal to negative 1. This one right here. This is where we're going to use this. Let's just do this via example, shall we? So let's say that we have, I don't know, let's call the complex number z 2 minus 3i, okay? And let's say the complex number w is 4 minus, or negative 4 plus I. How about that? Okay. Then let's do z times w. Well, we just write them next to each other. 2 minus 3i times negative 4 plus I. Okay. And what we're going to do is use that 4-letter word. You know, when you're multiplying binomial expressions together, there's a 4-letter word. It starts with F. You love doing it. I know it. I have too much dignity to say it out loud. The way I would say it is you're going to expand this thing out using the distributive property. So I sort of diagrammatically express this state of affairs like this. Okay. Well, if we expand this out, what do we obtain? So 2 times negative 4 is negative 8. 2 times I is 2i. Negative 3i times negative 4 is going to be positive 12i. Make sure you understand how that happened. And then finally, we have negative 3i times I. So I'm going to initially write this as negative 3i squared. Very sensible, right? It's kind of like I'm treating I like a variable. Okay. But of course, what we know by the properties of complex numbers, and this is the whole point, again, is that I squared can be replaced by negative 1. So we can make that replacement right here where we see I squared. And if we do that, we obtain negative 8. I can collect 2i and 12i together to get 14i. And then I have negative 3 times negative 1, because I squared is negative 1. But that's plus 3. And if I put all this together, I get negative 8 plus plus 3, which is negative 5. That's correct. Plus 14i. That's the product of z with w. Okay? And that's how multiplication works. It's pretty straightforward. You just carry it out using the distributive property. Okay. What is the effect of... Let's take a look at the following. Let's take, how about... Let's take I times... how about, well, let's start real easy. How about I times 3? Okay, so we have two complex numbers here, I and 3. What's the product of them? You'll be totally unsurprised to learn that this is 3i. I don't even know why I did that. And of course, we could write this as 0 plus 3i, but why would we ever do that to ourselves, right? 3i. What is the product of I and, let's say, 3i? Well, this becomes 3i squared, which is negative 3. Okay? I have a point that I'm trying to make here, but just bear with me, okay? What happens if I take, let's take a totally different thing. What happens if I take I times 1 plus I? What does this become? Well, I distribute the I, and I get I plus I squared, but I squared is negative 1. It's a real number. So I can rewrite this as negative 1 plus I. Okay, and finally, let's just do one more. Let's do I times, I don't know, 2 minus I. I think I mean it. Let's do negative 2 times negative 2 minus I. What is this equal to? This is equal to negative 2I. Now, I times negative I, think. It's negative I squared. But I squared is negative 1. So this is 1 minus 2i. Now what I'm going to do is I'm going to plot each of these numbers here. So notice the pattern that we've got here is that we're multiplying each of these numbers in red by the number I. Okay? And I claim that this has some kind of geometric effect. That multiplication by I does something geometric in the complex plane. So what I'm going to do is I'm going to draw a complex plane here. I'm going to try to draw it nicely so that we can see the geometry well. The horizontal line is tracking the real part. The vertical line is tracking the imaginary part. And I'll plot each of these numbers. So first of all, 3. 3 is right there. We can all agree, right? Now, where's 3i? 3i is right here. This is the number 3i. Maybe what I should do is track the products in a different color. So let me undo this, and I'll track the products in purple. Here are the products that I'm going to track. So yeah, 3 is right there. The product of 3 with I is 3i. Unsurprising. Nothing strange about that. Okay? So this red dot goes to that purple dot under multiplication by I. Okay. Wait, what? I forgot an equal sign here. That's weird. I should have put an equal sign right here. Negative 3. So this purple dot Oh, I don't like the way I'm doing this. Can I change things? I'm going to change, just for the purposes of my picture here. I'm going to change this 3 to 5. Just deal with it. I times 5i is 5i squared, which is negative 5. Okay, so now I can do this. Track in red, here's 5. And then in purple, this goes to negative 5i, which is over here, negative 5i. Okay. Then in red, I have 1 plus I. So where's 1 plus I? 1 plus I, oh, it's so close. It's like right here. And then where's the, when I multiply by I, where does this go? It goes to negative 1 plus I. That's right there. Huh. And then we have negative 2 minus I in red. Negative 2 minus I in red. There it is. And this goes to 1 minus 2I. There. It's kind of hard to see the pattern, but let me try to show you what's happening here. So here's 3. Let's just go back to this one. When we multiply 3 by I, we get to 3I. Okay, stop it. So we get this sort of going to here. When we had 5I, we multiplied by I. That went to negative 5, so it kind of goes down like this. When we had 1 plus I right here, we multiply that by I, and we go to negative 1 plus I, so it feels like we're going like this. And then finally, when we had negative 2I, negative 2 minus I rather, and we multiply by I, we sort of go around like this. Okay? Do you see what's going on here? I don't know if this is clear at all to you, but what's happening is that these complex numbers are being rotated through by an angle of 90 degrees. Okay? By an angle of 90 degrees. That's the idea. This is a 90-degree rotation. This is 90 degrees here. Oh my god, I find myself using heathen units. 90 degrees and 90 degrees here. Pi over 2 radians. My excuse is that I'm... Never mind. Oh, never mind. Oh, that was... I was about to say something deeply offensive. But yeah. In other words, multiplication by I corresponds to rotation by 90 degrees. That's sort of what we're observing here. Multiplication by I corresponds to rotation by, and I'll use non-heathen units here, pi over 2 radians. Yeah. And indeed, this is a huge reason why complex numbers are so useful, is because the multiplication by a complex number corresponds to has as an aspect of it rotation. We see that coming out in this particular example where multiplication by I corresponds to a rotation by 90 degrees around the origin of the complex plane. So phenomena in the world, in the universe, where rotation is sort of part of the process, are oftentimes really well modeled using complex numbers. And further, you can go even further than that. Because rotation has a kind of periodic behavior, rotation by 2 pi is the same thing as doing nothing. That periodicity also makes complex numbers eminently useful because we see periodic phenomena in our universe. For example, the sound that's coming out of my mouth and coming through transmitted into bits and then transmitted on your end, and then coming out by pushing air, your speakers pushing air in a certain way that is picked up by your eardrum and all those kinds of things. The pushing of that air can be broken down into sinusoids and that sort of thing. In other words, periodic objects, okay? And complex numbers come in real clutch in modeling those things, okay? Complex numbers are incredibly important. They are baked in to the universe, so you should I hope you feel some excitement to get to know them a little bit better, and we are definitely going to have occasion to do that. But let me end this video here. What have you learned in this one? You've learned what a complex number is, okay? You learned about what the real part is, what the imaginary part is, how to visualize them through the complex plane, this thing. Okay, you learned how to add them together. I gave it very short shrift, but I think it's very common sense. You learned how to multiply them. Just use the distributive property, okay? And then finally, you've gotten some inkling as to the geometry of arithmetic in the complex plane. And in particular, multiplication by I corresponds to rotation by an angle of pi over 2 radians. Okay, see you in the next one.